Are you ready for intersection of lines? Because October's awake, so you know it's going to be good. We're really zoomed in, so the camera quality. Oh, she's done. She's checked out. She lasted about 5 seconds of this video before checking out. Hopefully, you can last longer. Let's talk about line intersections. So, any two lines are going to intersect exactly once unless they're parallel. If two lines are parallel, well, either they'll never cross, or let's look at these two lines. They cross infinitely often. Right? If they're the same line, they have infinitely many intersections. Fun fact, by the way, this is only true in Cartesian coordinates, XY plane. You talk about spherical coordinates like the globe or something, then parallel lines can behave differently. Or lines can cross more than once, right? Think of the equator and like something that goes around the globe vertically. Those are two lines that actually cross twice. You're on. Anyway, that's weird non-Euclidean geometry, which we're not going to talk about. In this class, two lines are going to intersect exactly once, unless they're parallel. So if they do intersect, there must be a place where they have the same point, right? So if I have two lines, maybe one line looks like this, maybe the other line looks like this. Here's their intersection. Well, they both have that point. What does a point on a graph mean? It means it satisfies that requirement. So both of their inputs will satisfy both of their outputs, and their inputs and outputs are going to be the same. So how we solve this is we set their outputs equal to each other, and then we find what input does that for both of them. So let's do that here. Find the intersection of these two lines. Set their outputs equal to each other is how we're going to start. Well, h of t is the output of one, j of t is the output of the other. So h of t, that output, must equal j of t, that output. And now let's solve for the input that makes this true. In this case, we're going to solve for t. Since this is a linear equation, we're going to get all the t's on one side and all the numbers on the other side. I'm going to add t to both sides. On the left-hand side, we have 3t and another t. Now we have 4t. On the right-hand side, they just canceled out. Now we need to get all the numbers on the other side, so we'll add a 4 to both sides. The left-hand side, they cancel. Right-hand side, we have 5 plus 4, which is 9. We need t by itself, so divide by 4. We're going to get t as 9/4. That's fully reduced. You could also write that as 2 1/4. You could also write that as 2.25. They're all good. All right. And, I got ahead of myself. This is the input that makes this true. But we also need to find the intersection. We need an input and an output. Okay, solve for the input and then find the output. The question for you, I want you to think about, does it matter? And if so, how do we choose? Do we plug this into H? Or do we plug this into J? It shouldn't matter because they should have the same output. So you can plug it into either one. I'm going to choose J here because J looks easier. So J evaluated at an input of 5/4 is 5 minus 5/4. Or if you wanted to make, maybe you're better at decimals, 5 minus 2.25, and you'll get 2.75. Or 2 3/4, or 11/4, doesn't matter. So we're going to say they intersect at an input of 2.25 and an output of 2.75. I don't care what form you use but just be consistent. So if your input's a decimal, your output should be a decimal and vice versa. Let's check our answers. 3t minus 4. Where does that intersect to the other graph of 5 minus t? Oh, look at that. It intersects right where we thought it would. Good. All right. I want you to try it now. Look at this graph below, which, by the way, this graph is the graph that we just did. These are the same h, the same g, j. So look at those lines and answer the following questions for j, specifically for the green j, which is confusing because my name's Jay, Jason, and I'm wearing blue, but it's fine. Answer these, pause the video. Let's see if we get the same. What are the vertical intercept coordinates for j? Well, 0, 5. What are the horizontal intercepts for j? Where does it cross the horizontal axis? In this case, t, the t-axis. What are our t-intercepts? That's 5, 0. What's the slope of j? This one you have to be a little careful. Let's just pick some points. We got a couple points. We could say the slope is, well, we go down 2 and right 2. So the slope is down 2, right 2. Or you could go down 3, right 3. In either case, you're going to get the same answer because what does this reduce to? -1. Our slope for j is -1. Is j parallel to h? They kind of look parallel, right? Kind of, maybe not quite. I don't know. Graphically, I'd say no, but we can double check. I'm going to write no here right now. Oh, it's definitely not parallel. Definitely not parallel. They don't look anywhere close to parallel. And I'm going to guess that they're not perpendicular. Sometimes it's hard to tell. But if you wanted to check, well, the slope for j is -1. And the slope for h, we know that's +3. Oh, it's not close at all. Oh, this brings up another good point. So the negative reciprocal, right? Reciprocal of this is 1/3. But a negative? Negative 1/3? No. And you could go the other way, right? The line perpendicular to this, the reciprocal of 1 is 1. The negative of -1 is +1. So it'd have to be a slope of +1. +1 and +3 are not the same. So it's not even close to perpendicular. Why does it look close? Look at our grid here. Our grid here is not squares. So really watch out for this if you're graphing something on Desmos. So our grid here is squares. So it's easy to tell whether something's perpendicular or not. It's easy to tell these aren't perpendicular. And when we have squares, notice these lines are very not perpendicular, right? There's no way this is a 90-degree angle. But if we're looking at a view window that looks like this, for example, or like, right, a viewing window that looks like this, it changes the shape, right? Changes the shape. So depending on what our viewing angle is, if these aren't squares, it'll make it either look more perpendicular or less perpendicular. All right. And so on. And some viewing angles make them really not, right? And if I wanted to, I could actually choose a viewing angle that did make them look perpendicular. But you really have to check whether these are squares or not to visually inspect it. So something to watch out for. Is j increasing, decreasing, or neither? Remember, that always talks about left to right. You have somebody walking on J from left to right. Are they going up, down, or neither? They're going downhill. Decreasing. Because the slope is negative. And the person's walking downhill. Hopefully those are the answers that you got. Let's use these functions again and say, when is h bigger than j? Whenever you see a question like this, and there's an applied question of this on the homework. Whenever you see a question like this, for continuous functions, we'll talk more about in business calculus, one's always going to be bigger, and it switches maybe where they cross. Okay, so the only time it can switch for continuous functions, and most things in this class will be continuous. Continuous just means connected. So a line is all connected to itself. A piecewise function is not continuous. It's not connected. But if we have a continuous function or a connected function, and definitely for lines, if a function is continuous or connected, it can only switch at the intersection. Their value, I don't know a clear way of say it. Only switches, I'll just say that. Only switches at intersections. And even that's a maybe. So to find out when is h bigger, what we're going to do is find out when they're equal. So we know h of t is equal to g of t. Their function values equal. The intersections happens, well, at their intersection, which is, we said when t is 2.25. Let's look at the graph now. I'm going to make things a little clearer for you to look at. Here's what I mean. To the left of this point, j is bigger. To the right of this point, h is bigger. Everywhere to the left, j is bigger. Everywhere over here, j is bigger. And it can only switch who's bigger if they intersect for continuous functions, which is what we're dealing with. So we can visually inspect and say, okay, this is where it switches. J is bigger on the left. J is smaller on the right. We're curious, when is h bigger? The blue is bigger to the right of that. H is bigger. On the interval, 2.25 up to positive infinity. Everywhere to the right, h is bigger. Okay. I want to do a quick, let's do one more quick example of this. Okay. Let's look at two more functions. If I asked, when is C bigger than D? All we have to do is find the intersection. Where does C cross D? And then we can answer the question. Okay, so that's what you're looking for in this video. Let me know if you have any questions. I'll do an example problem of that with an application in the more practice video that's coming up right after this. So if example 10 doesn't really make that much sense, watch on and I'll cover it there. Let me know if you have questions and have a good one.